Hello guys, we're back with another video. Let's discuss electrolysis. Electrolysis can be defined as the chemical change in a liquid due to the flow of current. We're going to focus solely on the Faraday's laws of electrolysis. The Faraday's law of electrolysis states that the mass of a substance liberated or deposited during electrolysis is directly proportional to the quantity of electricity passing through the electrolyte. Now, when we say it's directly proportional, it means that the values, mass and quantity of electricity move in the same direction. So if you increase the mass, definitely the quantity of electricity will increase. But then let's take away the sign of constant proportionality here. Let's introduce equal to and introduce a constant z. All right. Now, Q is a quantity of charge, and the quantity of charge equals IT. That's current times time, and then you can swap this depending on whatever you need. So that means we can slot in this for this. So this becomes mass equals ZIT. Now you might be thinking right now, this Z we introduced, what does Z stand stands for? That's electrochemical equivalent, which is measured in kilograms per coulomb, or if you're given in grams, that'll be grams, per coulomb, right? And then the mass of substance deposited during electrolysis depends on the density. Depends on the density of the substance, the surface area of the cathode, and the thickness of the substance deposited on the cathode. You know, the way you've got your electrolytic cell. Let's just draw something. So in here, got your electrolyte. Let's say this is positive. Let's say this way. This is negative. This is positive. Your positive is the anode, and then the negative electrode is the cathode. All right. So mass in itself, as mentioned earlier, equals density times area. We're building up something here times the thickness. All right. Now, where did we come about this? You know, initially, density equals mass over volume, and then we made mass the subject of the equation. Area times thickness, that's the volume. All right, so just keep track of this. Just basic substitution, that was what we did. And then if I were to put this in equation terms, that would be mass M equals density times area times the thickness. All right, and then we know that mass equals initially electrochemical equivalent, ZIT times current times time. You have this. So if this equals this, that means you can substitute this, guys. So that would be density times area times the thickness equals ZIT. All right, so that solves the first law. The first law of Faraday's first law of electrolysis states that the mass of a substance, which I showed you guys right here. So what you have here is the first law of electrolysis, or we can put it as Faraday's first law. Yeah, Faraday's microfarads, first law of electrolysis. All right, so let's solve a question on the first law. Let's say we have copper. All right, let's say we have copper of mass 0.33 grams. All right, so this mass of copper, was liberated by passing 100 coulombs. 100 coulombs of electric charge through a copper voltmeter. Now the question says calculate the mass deposited when a current of 2 amps is passed through the voltmeter for 5 minutes. 5 minutes, and then I have to convert this to seconds. 5 times 60 seconds. I guess that makes sense on the sun. So what are we asked to calculate? We're asked to calculate the mass. So you can go ahead, pause this video, and then see if you can actually solve this question. All right, so let's name our values. Now Z, which is the constant, is 3.30 times 10 raised to the power of minus 4 grams per coulomb. Now I should have stated this earlier. It's a constant. All right, it's a constant. It has this particular value of the electrochemical equivalent. All right, so let's slot in everything we've got right here. So we need the mass. The equation that can get us the mass of copper deposited after passing the current is ZIT, and that is 3.30 times 10 raised to the power minus 4 times 2, which is the current, times 5 times 60. All right, that would definitely give up 0.198 grams. Easy peasy. Easy peasy. Let's say we have another question that says a charge of 1 coulomb. All right, let's deal with this. The electrochemical equivalent, which we have as ECE. Okay, let's do it this way. And I think we're done with this particular question, so we can take this off the screen. Yeah. All right. So we have the electrochemical equivalent, which is Z. That's 0.0033 grams per coulomb. All right. Now, a charge of 1 coulomb liberates 0.0033 grams. That's the electrochemical equivalent we have been given right there. Then there's some questions you might not be given. Yeah, you just take note of that. You might not be given, but depends on what the question is saying, if you're going to use it or not. But in most cases, you will definitely need it since it's a constant. All right, we have the current, that's 2 amperes, and then we'll have the mass, that's 1.98 grams, given from the question. So what exactly are we asked to calculate? The time, how long it will take, the time in seconds. So that will be M equals ZIT. All right. T will be the mass over ECE times I, and that gives 1.98 over 0.0033 times 2. That's 300 seconds. All right. Oh, well, if you wish, you can convert it to minutes. That's divided by 60. That gives 5 minutes.